quantum computers, what is this all about? Well, it must be something important because this is where we start. All these countries are investing quite a bit of money, okay, in developing quantum computers. They're investing all kinds of money in both private and government. It turns out that these numbers that you see there, that's for private, that's what's out there. Then you have the other stuff, the secret stuff that governments are doing in relation to quantum computing, but that doesn't get out there in the press. You know, it's held under national security. Okay, so these are just the outward numbers. Okay, and you can see United States, China, and then you have a whole bunch of countries that form, especially the European Union. If you take all those together, just the western part there, they're more or less as big as the United States and China. So there's a heavy investment in quantum computing. Okay, and you say, well, why? Why would anyone want to do quantum computing? I mean, the computer you have at home, it's known as a classical computer. You have a 19th century computer there. Okay. You know, it's classical and it works just fine. It gives you more or less the speed. Sometimes you get problems. Yeah, I've had problems. Feel like smashing them to pieces. But it works okay. I mean, you know, it's good. Do I need a quantum computer? And if I do, why would I need a quantum computer? What is a quantum computer about? What are we doing all that? Why are these people or these private and government agency or organizations, why are they investing in quantum computer? You say, what's the future? Well, what do we mean by that? What's going on here? Okay, and so here is, in a nutshell, what this is all about, okay, what quantum computers are about. And what they do is they're faster computing. Okay, that's probably the main point. It just does calculations a lot better. And so for some businesses or some lines of work, it helps. Like, for example, it helps chemists develop chemical modeling. It creates new materials with programmed properties. And then you have high temperature, superconductivity, and superfluidity. Okay, so it's used in these general areas. Those are any businesses related to this kind of work. They would like to have quantum computing. Now, does that help you in any way? Well, other than speed, you know, maybe quantum computer is not for you. You know, I mean, yeah, I'd love to have a faster computer that as soon as I touch that key on the keyboard, it boom, it does something already, you know, or has more memory or whatever. Right now, I can live with what I got, more or less. I could get maybe a better computer, sure. But do I need a quantum computer, super duper computer that, you know, takes me to the other side of the universe and back in a second? Okay, maybe I do. I don't know. Maybe it'd be nice to have. We got to wait to see until they develop it. So, what is all this about? What is really the question I want to answer today? Okay, because this is what we're about. We're not interested so much in technology. In fact, not at all. We're interested in science here. And so here's the question. Okay, question that I'm going to try to answer today. So if you came here to know a little bit about technology, you might be disappointed. Okay, sorry. Okay, and so here it is. This is the question I want to ask, or that I'm going to answer today. I'm going to try to answer today. Do quantum computers have anything at all to do with science? This is about science. We call it rational science. We want to do science here. And this issue came up because a fellow asked about this in one of the questions, so I turned his question into the lecture. Okay. Okay. So what is this quantum computing? What are we talking about here? Okay. Here it is in a nutshell. Okay. This is just a quick synthesis of what quantum computers or quantum computing does, what we expect from it. Quantum computing is the exploitation of collective properties of quantum states. You know, there's 50 states in the union. I don't know of any quantum state, but that's what they're talking about. What are these quantum states? What are we talking about? Such as superposition and entanglement. Okay, so we have superposition and entanglement. These are two quantum states. And what are we going to do with this? Well, it's going to take, the quantum computer is going to take advantage of these properties, behaviors. Okay, love it. Okay, let's find out. To perform computation. Okay, they solve computational problems substantially faster than classical computers, which is what I got. I got a 19th century computer, a classical one. Okay, since quantum came around, you know, 20th century and upwards, well, we have now quantum computing. Okay, so essentially it's going to be faster. That's the bottom line. Some line items out there of the economy and some lines of work, they might require this speed for other reasons that help them develop more technology. But for me, or for you, it's probably just going to be speed. Fine. We welcome speed, no problem at all. But the question is, are quantum computers, is quantum computing a part of science? That's the issue we're going to answer. And here they're talking about two quantum states of which quantum computers take advantage, which are entanglement and superposition. So we got to get to the heart of those. We got to get to the bottom line there. Okay, here's superposition. Okay, and then put it up here. If I can get it there. Here's superposition. Okay, and you can see what it is. In quantum, an atom can be excited and not excited at all, both simultaneously. How do you explain that rationally to a human? That you have these two states in one. In one where you can even call it standing still and moving. Can you do that at the same time? Can God be a concept and an object at the same time? Can he have shape and not have shape at the same time? How would you understand that? And same thing here. I mean, here it's got two superimposed states. One in which, it's got these two states, these two vibrations simultaneously. How can you explain this? I mean, maybe the guy can explain it, I don't know, but I don't know if a rational human can understand it. What is he talking about? I mean, this is just a statement. This is just saying it is so. Well, that's a description. You haven't told me how it does this. What is the mechanism? Okay, so this is superposition, okay? Founded on that, before we move on to entanglement, okay, which is the other state that they are going to take advantage of, we got to understand this notion of the qubit. Okay, what the hell is a qubit? That's along my line of work. I worked in semiconductors, chips, okay, not potato chips, transistors, that sort of thing, semiconductors, okay. And this is along the same line. They say there are several types of quantum computers, quantum computing systems, okay. And the most widely used model is the quantum circuit, okay, based on the quantum bit or qubit, okay. So this is an important point that underlines especially the superposition aspect of quantum mechanics. It's known as the qubit. What is the qubit? Okay, a qubit can be in a 1 or 0 quantum state. Okay, what is this 1 or 0? I explained it in the past. I'm just going to go briefly here. A transistor is either on or it's off. Okay, so if it's got, for example, more than half a volt, it's on. If it's got less than half a volt, it's a 0. And so you have all these lines crossing at a transistor. You have maybe the aluminum bus lines. You got the polysilicon lines crossing them. And if they both carry a voltage that's over 5 volt, half a volt, then you have that transistor turns on. If it's less than that, it's a 0. So how can that transistor be both a 0 and a 1? This is the question. It's mind-boggling. How are you going to explain that the transistor is both on and off at the same time? Okay, let's continue. Maybe we find the answer. I don't want to prejudge. They're smarter than me. Okay, when it is okay, so it says a qubit can be in a 1 or 0 quantum state or in a superposition of the 1 and 0 states. Okay, great. Okay, when it is measured, it is always a 0 or a 1. Okay, only when it's measured. Before you measure, okay, it's going to be in both quantum states. So you see it there at the bottom. Under the classical computer, the transistor is either a 0 or a 1. We're down. We can't have it both. It's either 0 or the 1. But under the quantum computer, it's going to be both. Before you measure it, before you use it, before you do something with it, it's going to be in a 0 and a 1. So in the left, it's going to be 0 or 1, and the right is going to be a 0 and a 1. Okay. The probability of either outcome depends on the qubit's quantum state immediately prior to measurement or usage or whatever. So before you use it, it's going to be in this 0 and 1 state. Okay. And so let's get to a little more into the definition of what a qubit is so that we understand this exactly what they want to say. They say a qubit, the basic unit of quantum information. And again, it's what they're talking about is a transistor in real terms. Okay, that's what we're talking about. A qubit is a two-state quantum mechanical system. It exhibits the irrational physical interpretations of quantum mechanics because it's going to use entanglement and it's going to use superposition, which is what we're covering here. Okay. In classical mechanics, a bit is in one state or the other, but in quantum mechanics, the qubit is allowed to be in a coherent superposition of both states simultaneously. See what these people are saying? You got a 0 and a 1 both at the same time. You have a transistor that is on and off, not or off, on and off at the same time before you measure it. Okay. My God. How do we explain that? Well, here's the explanation, that the typical explanation for this phenomenon. and it's known as Schrodinger's cat um, analogy, I guess that's what they call it. Okay, here it is. Okay, and what is it? Well, the cat, before you peek into the box, because you had, some poison in there in a vial, and it turns out that you're going to have a hammer break it, and this radiation comes out and kills the cat. But you don't know what's happening in there because you haven't looked in the box. It's when you open it, when you take the measurement, in other words, when you use your eyes, when you do an experiment, you go see and touch at the lab. That's when you know whether the cat is in one or the other state. It's either dead or it's either alive. That's how it comes out of the box. Okay? But before you peek into the box to find out what really happened inside there, the cat has both states. He's both dead and he's both alive. So I always ask, well, what if we remove all this other stuff that killed the cat? Okay, before we peek inside the box, is the cat alive or dead? I just put a cat in a box. He's alive. I don't open the box. Is he alive or dead in there? And these people say that quantum says he's both. And that's more or less the big problem we have here. There is no way to understand this under any circumstance. Not for a rational human being. Now, a mathematician, he's different. I mean, he can understand this stuff, but human beings cannot. Okay? Okay, so how about entanglement? Well, here's one fellow on the internet, prominent guy, and he has a little video there on YouTube. It says, entanglement, the quantum around you. And he says, from the start, he's going to talk about entanglement. The first thing he says, I'm not going to be able to really explain what entanglement is. We don't know what superposition is. We cannot explain it in a rational manner. We have no idea what entanglement is. They cannot explain it in a rational manner. He's telling you, he's confessing up front. He's giving you the fine print up front, saying, oh, by the way, I cannot explain entanglement. And you say, well, why can't he? I mean, what is this thing, entanglement? Okay, so let's illustrate it so we know what we're talking about. What is entanglement? Here it is. I've shown this in the past. Here you have two atoms, or whatever, two particles, you can say. They're on opposite sides of the universe. So they're 100 million kilometers or 100 gazillion kilometers apart. And these people are saying that if one is moving clockwise, the other one is definitely moving counterclockwise in the other side of the universe. And if you happen to turn the first one from clockwise to counterclockwise or vice versa, the other one moves instantly in the opposite direction. Okay, so this is what quantum entanglement is about, and they say they have no explanation for this. And let me tell you why they don't have an explanation. And under the rope model, we can see why, and we can see also the answer of why this does happen. And here it is. Okay, the one on the top is the quantum version. There's nothing in between the two particles. So yeah, we cannot explain how one particle influences the other one instantaneously. And what they're saying is, well, it doesn't do that really. What it happens is, before you take the measurement, we already know, Mother Nature, Father Universe, God, whoever, the devil, one of those guys has already determined that the guy on the other side of the universe is opposite to the one on this side of the universe. It's already like that. Okay? So it doesn't matter if your particle is moving clockwise or counterclockwise. We know already through quantum, because Father Universe determined so, that the other one is in the opposite direction. The one is spinning in the opposite direction. Okay? And so when you take the measurement, you know not that something happened instantaneously across the universe, but you know that the other one is already moving in the opposite direction simply because it is so. Okay? Under the rope model, it's very simple. You know, a rope can spin in one direction clockwise or counterclockwise. If it's spinning clockwise from your end, from the other guy's end, it had better be spinning counterclockwise. See how easy it was? Yeah, you have to have a mediator to explain it rationally. And, I always have my rope, and I'm saying, let's see if I can do this right. For you, I think it's moving clockwise, because for me, it's moving counterclockwise. And if I move yours counterclockwise, okay, mine is now moving clockwise. So a rope can only move in one direction or the other one direction. And you say, well, can it do instantaneously? Isn't there like, I twirl my side of the rope until that signal reaches you? Is it still spinning on your side in the same direction as mine? Well, it's a little more complicated than that. You have ropes, electromagnetic ropes that are tied from the Andromeda galaxy to 0.2 to 2.3 million light years away. And those are spinning, let's say they're spinning clockwise, okay? That rope is still spinning clockwise, and when you measure, the question is, are you measuring a single rope? Okay, are you affecting that rope? Or is that one just crossing by and going to another star somewhere far away? So the fact that you can tune into that because that rope happened to cross your atom and you happen to measure it and you're doing clockwise on that, is that the same rope you measure the next second when you take a measurement again, especially when the Earth is moving around the sun and all the atoms in the universe are moving everywhere? So it's a little more complicated than that until we try to explain the phenomena and we try to simply state that, oh, it does so, like they do so in quantum. We don't have an answer to that question. The only way we can do it is we analyze what we're doing in the lab, and we can't do that by seeing and touching because we can't see or touch the mediator of light. We can barely handle one atom at a time, which these people many times claim. The question is whether that is so. Are they doing that? Can they see an atom? If they can't see an atom, how do they know they're handling one at a time? Is this just their theory, their conclusion, their inference? Okay. Are they just concluding this? So there's a lot involved in that, and it's got to be done with rational people sitting down and exchanging ideas how entanglement is happening. But at least they have a starting point, which is, a rope can only turn clockwise or counterclockwise. That's it. And then we have to figure out which rope we're measuring at which time and whether everything moved in between. Okay, are we measuring the same rope? Okay, and then, a lot of the ropes that crisscross an atom, let alone the universe, but an atom, they're spinning in every direction possible because you have ropes that are counterclockwise, ropes that are clockwise, that are just going through an atom from a faraway star to another faraway star. So you got to look at what you're really doing, what you're measuring. These people measure and they don't even know what they're measuring because they can't see or touch the thing, and they say, oh, we've reached this conclusion. Well, yeah, that's based on the particle hypothesis. And of course, they cannot explain it with a particle hypothesis. So what does this guy say? Well, I cannot explain entanglement. Well, if you cannot explain entanglement, you're not a scientist, because what is science? Okay, or for that matter, superposition. You cannot explain superposition in a rational manner. Well, you got a problem, because what is science? And here we have it. We can put this thing up there. Here it is. Science, a systematic enterprise that builds and organizes knowledge. And this is their definition, not mine, by the way. I don't subscribe to this definition. It's got too many problems. But, we're using their own definitions here to find out if, under their definition, quantum computing, qubit, entanglement, superposition, if those qualify as scientific behaviors or explanations or whatever. And it says that builds and organizes knowledge in the form of what? Testable explanations and predictions about the universe. And so if they cannot explain in a rational manner, how can they test the explanation? What they're testing is the description. They're describing something, but they're not explaining it. And so no, entanglement and superposition, which underlie the qubit, okay, which underlies the quantum computing world, is not a scientific field. Anyone who gets into that is a technologist, not a scientist. And there you see technology. What is technology? Again, their definition: the sum of techniques, skills, methods, and processes used in the production of goods or services, or in the accomplishment of objectives. Okay, we define it a little differently. We say that technology is developing gadgets by trial and error. Science is something else. What is science? Let's find out, and we'll find out in our conclusions here. Science is explanations. Okay, and here it is. Okay, these are my conclusions. Quantum computing has to do solely with technology. Okay, essentially faster computing. That's it. And a marketable word quantum is inserted to solve the concept. Okay, so they say, oh, it's not just a computer, it's quantum computing. And they say, oh, a lot of people out there will say, oh, the scientists have proven quantum. And how do you know? Well, you wouldn't have a computer if it weren't for quantum. And for sure, you wouldn't have a quantum computer if it weren't for quantum. And no, they're not talking about science. They're not talking about explanations. They're talking about technology, which has absolutely nothing to do with science. Why? Because science is explanations, and technology is developing gadgets by trial and error. Okay, so if you develop a gadget, in your lab, yeah, you don't have to know how it works really, or the underlying causes or mechanisms of the invisible stuff that underlies it, like magnetism or electricity. You don't have to understand the true, genuine mechanism that underlies light, gravity, electricity, magnetism. You don't have to understand that. You can develop the gadget because you have to do something that is handled by touch, which is what technology deals with. Technology deals with the see and touch. Science deals with the mind, with explaining rationally. That's where the difference is. Okay, so quantum has no rational explanations, physical interpretations for what? For entanglement, superposition, decoherence, qubit, none of that. They don't have a rational explanation. They have descriptions, and they tell you up front, we cannot explain it. We have no physical interpretation that you can understand. We cannot rationalize it. So they're not doing science if they cannot rationalize it. They are doing descriptions, they're doing technology, but they're not doing science. And so there's the conclusion really therefore quantum computing has nothing at all to do with science, and anyone working in the development of quantum computers, quantum computing, is not a scientist.